Picture this. Our galaxy may hold around 6 billion Earth-like worlds, 6 billion chances for life to bloom. So why would one lonely object spend 2 million years crossing the dark just to arrive here, right as we build the tools to notice it? This is 3I Atlas. It is not behaving like a random comet. Its path tells a different story, a story of aim, not accident. Tonight, we are going to pull that story apart. If you want to follow every twist as new data comes in, subscribe and stay with this channel. For months, you have probably heard 3I Atlas described with comforting words. An interstellar visitor, a strange but natural comet from somewhere out in the galactic wilderness. A curiosity that just happens to be passing through our solar system on its way to nowhere in particular. That story felt safe because it treated this object like background noise in a busy universe. Interesting, yes, but not personal. Not about us. Then something changed. For 6 weeks, a small group of researchers quietly attacked the problem from a different angle. They did not start with guesses about what 3I Atlas is. They started with where it came from. They pulled together the sharpest measurements of its position and speed, linked up with multiple observatories, and began a brutal kind of cosmic rewind. Step by step, they ran its orbit backwards through time, letting the gravity of stars, planets, and the galaxy itself tug on it inside their simulations. At first, this sounds almost straightforward, like running a tape in reverse. In reality, it is closer to untying a knot that has been shaking for 2 million years inside a storm of 400 billion stars. Every small uncertainty in position, every tiny error in stellar motion, can grow into a huge mistake over such vast times. That is why they attacked the problem with multiple independent methods and why they kept rerunning the numbers, even when the answer stopped moving. Because when all those methods finally settled on the same result, the team faced a conclusion that did not feel safe at all. 3I Atlas does not point back to a random patch of empty sky. It points to a very specific region in our local galactic neighborhood. Not far by Milky Way standards, not anonymous. A place we already know hides something strangely familiar. That is the secret that shattered their sleep and the simple story we have been telling ourselves about this visitor. If you want to know where something came from, you follow its trail. In space, that trail is the path carved by gravity. 3I Atlas did not simply appear at the edge of our solar system. It fell in along a path that has been shaped for roughly 2 million years. Buried inside that path is information about its origin, the way a tossed ball remembers the hand that threw it. The trick is that space is not empty. Every star pulls on every other thing. Our galaxy is a storm of gravity. To rewind the journey of a single object through that storm, you have to recreate the entire gravitational weather of the Milky Way over millions of years. That is what this team set out to do. They took the most precise measurements ever made of an interstellar visitor. Exact positions on the sky, tiny changes in speed, slight deviations from pure gravity. Then they turned time around inside the computer. In their simulations, 3I Atlas becomes a point of light moving backward. The sun retreats, the planets unwind their orbits. Nearby stars drift to where they were in the distant past. At each tiny step, the code calculates every meaningful tug from every mass within about 100 light-years of the object. It is not a single neat equation. It is millions upon millions of small pushes and pulls, integrated in reverse. Dr. Sarah Chen at Berkeley led that computational assault. Her group refused to trust any single method. They built 3 separate ways to rewind the path. One used direct numerical integration, tracking the exact interactions of many bodies. Another scattered slightly different starting conditions in a Monte Carlo swarm to test what measurement errors might do over time. A third used machine learning trained on realistic stellar motions to fill in gaps in our maps of the local galaxy. If any one of these had produced a different answer, this would still be an odd comet. Interesting, but easy to argue about. That is not what happened. All 3 methods, with all their different assumptions and weaknesses, converged on the same picture. Run history backward, and 3I Atlas does not fade into randomness. It threads its way cleanly back to one small region in space, at a distance that matches roughly 2 million years of travel at the speed we observe today. When the simulations stopped rewinding, they did not point to some anonymous corner of the galaxy. They landed on a very specific address, roughly 270 light-years from here. At the speed 3i Atlas is moving, that distance matches about 2 million years of travel time. In cosmic terms, that is the next neighborhood over. Not halfway across the galaxy, more like a few blocks away in a city that stretches for 100,000 light years. In that neighborhood sits a star with a catalog name that sounds boring, but hides something remarkable. HD 43782. It is what astronomers call a G-type main sequence star, which in plain language means a near twin of our Sun. Its mass is almost the same. Its surface temperature is within a few hundred degrees of our own star. Its age is around 4.8 billion years compared to the Sun at about 4.6. If you could teleport to a planet there and look up, the daylight would feel uncannily familiar. Once that star popped out of the trajectory analysis, the team did something obvious and terrifying. They checked the exoplanet databases: Kepler, TESS, ground-based follow-ups. HD 43782 has been watched before. It already has at least 4 known planets. One of them, labeled HD 43782c, orbits right in the habitable zone, at almost exactly the same distance from its star that Earth keeps from the Sun. Its year is only a little shorter than ours at about 342 days. Its mass is just under Earth's, not a gas giant, a rocky world. And then comes the part that makes your skin crawl. Astronomers have already taken spectra of that planet's atmosphere. In the thin ring of air silhouetted against its star, they see the fingerprints of water vapor, molecular oxygen, methane, and carbon dioxide. On Earth, oxygen and methane do not play nicely together. They react, cancel each other, vanish. The only reason they coexist here is that life is constantly pumping them back into the air, plants and microbes locked in a never-ending chemical tug-of-war. So now line up the facts. An interstellar object whose path rewinds to this specific system. A sun twin. An Earth-like planet in the comfort zone. An atmosphere with the same unstable gas cocktail that screams biological activity on our own world. At some point, this stops feeling like coincidence and starts looking like a message about where 3i Atlas truly began. Once you know where the trail leads, you can ask a sharper question. If 3i Atlas came from that specific star system, did it leave the way natural objects usually do, or did something push it out on purpose? Nature already gives us a way to throw rocks into interstellar space. When multiple planets and smaller bodies dance around a star, their gravity can fling comets out at high speed. We have seen it in our own simulations. We have seen the end products drifting through the galaxy. Those ejections come out like sparks from a fire, flying in all directions with all kinds of speeds. The team put 3i Atlas under that lens, and the pattern did not fit. Its incoming path is not a random spark. It approaches almost straight toward the plane of our solar system from the direction of that sun-like star. Its speed before the recent slowdown is strange as well. Faster than you would expect from a simple gravitational kick, yet slower than you would choose if you were trying to cross the galaxy quickly. It looks as if something pushed it just hard enough to reach us in roughly 2 million years, then turned off and let it coast. To test that idea, they compared it to another famous visitor, Oumuamua, the first interstellar object we ever saw passing through our system. Oumuamua came in on a path that screamed natural ejection. Its direction and speed matched what you would expect from a random chunk thrown out of a distant system. It sliced through the inner planets on a one-time flyby and kept going. No sign that anyone had aimed it at us specifically. 3i Atlas does not behave that way. Its trajectory lines up with a single known system that we already suspect hosts life. Its speed matches a deliberate launch 2 million years ago, better than it matches the messy scatter of natural ejections. On top of that, its later course. Changes near the sun look like someone or something has been fine-tuning the schedule as it arrives. Scientists are cautious by training. They looked for every possible way to blame these patterns on measurement errors or hidden biases. They invited independent teams to rerun the data and to try different models of the local galactic environment. Yet each time the answer slid back to the same unsettling place. This object behaves as if it was launched, not lost. That is the point where the story ceases to be about a weird comet and becomes a question about intention somewhere else in the galaxy. Once you accept that 3i Atlas was probably launched, another question steps into the spotlight. Why here? Of all the stars in the Milky Way, why send anything toward our specific system? On a trip that began when our ancestors were still chipping rocks into crude tools on the African plains. 2 million years ago, there were no cities, no telescopes, not even language as we know it. Just small bands of hominins trying to survive. Yet somewhere near HD 43782, something pressed the launch button. One possibility is almost bureaucratic in its coldness. Maybe they did not aim for us at all. Maybe they aimed for stars like theirs. If you live around a sun twin, it is reasonable to guess that other sun-like stars might host Earth-like planets. In that case, 3I Atlas could be one of many probes sent out along a grid of targets. Thousands or millions of missions fired toward familiar-looking stars, trusting that some will find interesting worlds. Under that view, our solar system is one line in a cosmic survey plan, comforting in one sense, unsettling in another. A second possibility feels stranger. Observation. Perhaps they did not fire blindly at every sun-like star. Maybe they already knew that our system was special because they could read faint hints of life in our atmosphere from hundreds of light years away. We are only just beginning to detect biosignatures on nearby exoplanets. They might have had that skill long before we walked upright. With instruments far beyond ours, they could see oxygen and methane above Earth and mark us as a living world worth visiting. The third option is the one that keeps people awake. Prediction. In this picture, they did not just see that Earth was alive. They calculated that Earth would eventually become technological. They ran long-term models of planetary climates, evolution, and geology, and then layered in some understanding of how often intelligent tool users emerge. From that, they picked out star systems that were not just alive now, but likely to host radios and rockets by the time a probe arrived. If that is true, then 3I Atlas is not a shot in the dark. It is the result of a forecast that said someone like us would be here now, ready to notice and analyze it. All three possibilities share a single implication. Our solar system has been on someone else's map for a very long time. Whether this probe is a survey instrument, a response to our first chemical whispers, or the product of deep predictive science, its arrival tells us that we have been seen. And that is a very different feeling from drifting alone in a quiet universe. Up to now, everything we have talked about could, in theory, have been decided 2 million years ago. A launch from a life-bearing system, a carefully tuned initial push, a long, quiet coast through the dark. That is already staggering, but the truly chilling part is what 3I Atlas has been doing recently. It is not just falling through our solar system like a stone, it is acting. As it approached the inner system, its motion began to change in ways that pure gravity cannot explain. Small but clear decelerations. Subtle shifts in course near perihelion, the moment of closest approach to the sun. These are not giant fireworks. They are precise nudges. Enough to slow the object down and bend its path so that it does not simply swing past and escape forever, but instead remains trapped on a bound trajectory near us. Those maneuvers look like someone adjusting arrival time and parking position after a journey that lasted longer than our entire genus. At the same time, radio telescopes started to hear something unexpected. On top of the earlier detections linked to ordinary comet gases, observers picked up a narrow signal near the famous hydrogen line, around 1.42 gigahertz. A frequency astronomers have long joked would be the natural hailing channel for anyone trying to get the attention of a radio-capable civilization. The signal repeats roughly every 47 seconds and carries a structure that is not just noise. There is mathematics in it, layers of encoding we do not yet fully understand. Put all of that together, and a very old idea suddenly feels very current. In the 1960s, the physicist Ronald Bracewell suggested that advanced civilizations might send out autonomous probes instead of relying on radio alone. These machines would travel to other stars, go to sleep, and then wait. Once the local life built radios and telescopes, the probe would wake up, watch, and respond. It would be a patient ambassador solving the problem of conversations that take centuries each way. Look again at 3I Atlas through that lens, a launched object from a living system, a long, silent drift. Then, right as our species becomes spacefaring and radio loud, it begins to break, to adjust, to broadcast, to stay. It is behaving exactly the way a Bracewell probe is supposed to behave on paper. Whether that is truly what it is remains unproven, but the resemblance is close enough to turn a theoretical concept into a living, moving question hanging in our skies. Try to imagine building something that has to work not for a century, not for 1,000 years, but for 2 million. It has to cross hundreds of light years in perfect darkness, stay mostly asleep the entire way, then wake up on schedule and start making decisions in a completely different star system. That is the engineering puzzle wrapped inside 3I Atlas if it is a probe and not a rock. Even thinking about that timescale bends the way we normally talk about technology. Our oldest surviving human structures are young compared to this journey. Start with the body. Space between stars is not empty. It is full of high-energy particles and dust grains moving fast enough to chip away at anything in their path. Over millions of years, those tiny collisions add up. Materials swell and crack. Electronics accumulate damage from radiation. On our own spacecraft, we fight those effects for decades, and we still lose. Yet whatever is inside 3I Atlas appears to have survived intact, long enough to perform precise maneuvers and broadcast structured signals after a voyage that makes our missions look like test flights in a swimming pool. Then there is the question of power. No battery we know could sit in the cold and wait that long. Radioactive power sources decay. Stars drift out of alignment. For something to coast between suns and still have energy left at the far end, it either starts with a source beyond anything we use now, or it spends almost all of its life in a kind of deep hibernation, waking only when conditions are just right. Maybe it harvests the faint glow of interstellar space, or, more likely, it waits until it feels the warmth of a new star and then drinks in light like a seed-breaking dormancy. On top of that sits the software problem. How do you write instructions that will still make sense after geological time? How do you design sensors and logic that can cope with the target civilization whose behavior and technology you could never fully predict? The probe has to detect us, recognize that we are interesting, and decide what to do next, all without a technician ever opening a panel. It has to be robust against unknown failures, unknown environments, and unknown minds. Even if we knew nothing about the launch system, nothing about the civilization that built it, the simple fact that 3I Atlas appears to function after such a journey would already be a message. It tells us that somewhere, sometime, someone mastered stability and endurance at a level we have barely begun to imagine. In that sense, the probe is not only carrying information, it is the information. A physical proof that technology can be stretched across deep time and deep space, and that in our galaxy we are not the first to learn how to do it. Up to this point, it is tempting to tell ourselves a comforting story. A curious machine from far away. A patient ambassador. A chance for contact and shared knowledge. That version feels good because it casts 3I Atlas as a friendly visitor. Yet once you accept that this object was launched, aimed, and is now active, you also have to face the shadow on the other side of that story. What if it is not here to talk? What if it is here to judge? We are used to imagining ourselves in the role of the explorers. When we send probes to other worlds, we paint them as peaceful scientific missions. It is an easy mental step to assume that anyone else who reaches the stars would do the same. Dr. Peterson at Stanford, who studies catastrophic risks, has a blunt answer to that. We are guessing. Our sample size for advanced alien civilizations is exactly 0. We have no data on how they behave when they find someone new. Think about what we already know. A civilization around HD 43782 or something in that system identified our solar system millions of years ago. They invested huge energy into building and launching an object that could survive an almost unimaginable journey. It is here now, maneuvering, broadcasting, staying close instead of racing through and leaving. That alone tells you they are capable of projects that span deep time and vast distances. Power, materials, navigation, all far beyond what we can currently do. If a culture with that level of control over energy decided we were a threat, or an opportunity, or simply irrelevant, what could we really do about it? The hard truth is that if they wanted to harm us, they could probably do it in ways we would not even recognize until it was far too late. That does not mean they are hostile. It means that in any encounter like this, the balance of power is wildly lopsided, and pretending otherwise is a dangerous fantasy. So we find ourselves caught between hope and caution. Maybe 3I Atlas is a kind of cosmic handshake, a patient teacher waiting to see if we are ready to learn. Maybe it is a survey instrument, quietly taking notes and sending home a report on what we build and how we behave. Or maybe it carries evaluation criteria we would not pass. We do not know. What we can say is that this object is not random, not blind, and not trivial. It forces us to think about our species the way someone else might be thinking about us right now. Discovery is thrilling, decision is harder. Now that we know where 3I Atlas came from and what it might be, the question shifts from what is it to what do we do? This is not a purely scientific puzzle anymore. It is a strategic choice with stakes that reach far beyond one research group or one space agency. The options on the table pull us in very different directions. The boldest camp says, go to it. Launch a fast mission while the object is still in the inner solar system. Rendezvous, fly alongside, take images no telescope on Earth could match, sample its surface, maybe even peek inside that strange, possibly hollow interior hinted at by its behavior. Direct study could answer questions that remote sensing will never resolve. What drives its propulsion? How does it power itself? What is actually broadcasting that signal? This is the path of maximum knowledge and maximum contact. It is also the path of maximum chance to trigger a response we cannot predict. Another group argues for patience. Keep our distance. Point every radio telescope. We have the narrow band transmission around the hydrogen line. Pour talent and resources into decoding its layers. Look for structure that might be instructions or protocols for how a conversation is supposed to start. In this view, rushing a spacecraft toward it before we understand the message is reckless, like grabbing a device whose safety manual you have not read. Decoding first gives us time to think and to coordinate a global answer. Then there are those who say we should dim the lights. Stop transmitting toward 3I Atlas. Stop pointing our best instruments at it in obvious ways. Act as though we barely noticed. Every signal we send, every maneuver we make in response, could be feeding it data about our technology, our coordination, our fears. To this camp, playing dead is the closest thing we have to self-defense when we do not understand what we are dealing with. Each path carries a different mix of courage and fear. Each could turn out to be wise or disastrous. There is no safe default option because pretending this is just a weird comet is also a choice, one that leaves us blind. The only thing we know for sure is that ignorance will not protect us. Whatever we decide next will say as much about who we are as a civilization as it does about the probe watching us from the dark. In the end, 3I Atlas is not just a story about one object. It is a mirror. It reflects back to us how we see ourselves and how small our imagination has been. For most of our history, we told a simple story about humanity, alone under a quiet sky, center of the action, the only minds in the neighborhood. The trajectory work on this object tears that story open. Somewhere out there, someone else looked up at their own sky and wondered if anyone was listening. Then they acted on that question in a way we have only begun to grasp. We now live in a different universe than the one we thought we lived in yesterday. Not because the cosmos changed, but because our information about it did. Data is being shared. Trajectories are going into peer-reviewed papers. Independent teams will test the simulations and try to break them. That is how science works. But even if the details shift at the edges, the broad picture will be hard to escape. This object came from somewhere specific. That somewhere almost certainly hosts life. And its arrival here is almost certainly not an accident. The question is what we do with that knowledge. One path is denial, treating this as a curiosity for specialists while the rest of the world scrolls past. Another path is fear, folding into stories of doom and inevitability. A third path, the hardest one, is to treat this as a moment to grow up as a species. To recognize that we are part of a larger community of minds, even if we have not met our neighbors yet. To admit how vulnerable and unprepared we are without letting that turn into paralysis. That means this conversation cannot be left only to astronomers or defense committees. It belongs to philosophers, artists, engineers, spiritual leaders, and to you sitting with a screen in your hand. It belongs to everyone who will live in the future shaped by the choices we make now. Do we lean into curiosity, into careful courage, into a shared sense of responsibility for how humanity introduces itself to the rest of the galaxy? Or do we look away and hope that doing nothing will somehow keep us safe? 3I Atlas has already crossed its distance. It has already waited its millions of years. The next move is ours. Whatever you believe about this object, the one answer that no longer works is that we are alone and unobserved. Someone else asked the same questions that keep us awake at night and sent their reply into the dark. Now it is here, hanging in our sky like an unopened letter. Ready or not, the age when we could pretend the universe was empty is over. What begins next is the story of how we choose to live in a universe that finally answered back.